If you hear the word transformer in the AI world, it can sound like a fancy brand name, but it's really a particular kind of model architecture that became especially important for working with language and other sequences. The reason Security AI Plus cares is that many modern generative systems, especially large language models, are built using transformers, and their security risks are shaped by how they process input and generate output. When you understand a few core ideas, attention, tokens, context windows, and limits, a lot of confusing behavior suddenly makes sense. You'll understand why a model can seem brilliant one moment and oddly forgetful the next. You'll understand why prompt wording matters so much and why long conversations can drift. You'll also understand why defenders worry about data spillover, prompt injection, and leakage, because those risks are connected to how the model handles context. This episode is not about coding or engineering. It's about building a clean mental model that helps you reason through scenarios and choose the safest decisions. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To start, a transformer model processes information as a sequence, meaning it looks at a stream of pieces of input and decides what patterns matter across that stream. In language, that stream could be words and punctuation, but the model doesn't literally see words the way you do. Instead, it sees tokens, which are chunks of text that can represent a whole word, part of a word, or sometimes a symbol or short phrase. Tokens matter because they are the units the model works with internally, and they affect how much text the model can handle at once. If you've ever wondered why two sentences that look similar can behave differently, tokens are part of the reason, because the model's internal representation depends on how the text is broken up. From a security perspective, tokens matter because they are part of the boundary of what the model can consider at one time, and boundaries create opportunities for confusion and manipulation. When an exam scenario mentions prompt length or conversation history, tokens are often hiding underneath that description. Understanding tokens helps you predict when the model might lose track of earlier details or interpret your input in an unexpected way. Now let's explain attention, because attention is the idea that gives transformers much of their power. Attention is a mechanism that lets the model decide which parts of the input sequence should influence the processing of other parts. In plain language, attention is how the model focuses on the relevant pieces of context when deciding what to generate next. If you write a long paragraph and then ask a question at the end, attention is what helps the model connect the question to the relevant earlier details. Without attention, the model would have a harder time tracking relationships across distance, like linking a pronoun to the noun it refers to or connecting a requirement at the top of the prompt to a decision at the bottom. This is why transformer-based models often handle long-range relationships better than older approaches. But attention is not the same as understanding, and it does not guarantee correctness. It is a pattern-based focusing system, and that distinction matters for security because an attacker can try to hijack what the model focuses on. A useful analogy is to imagine a spotlight that can move across the input text and highlight pieces that seem relevant for the next output. The spotlight does not prove truth, it just indicates influence. In a normal user interaction, that spotlight helps the model stay coherent. In an adversarial interaction, someone can try to position their instructions so the spotlight favors them over the intended rules. This is part of why prompt injection is possible, because if the model's attention is drawn to an untrusted instruction that appears persuasive or strongly formatted, it may prioritize it over safer guidance. In exam terms, when a scenario describes a model being steered away from intended behavior by user-provided content, you can connect that to attention and the model's dependence on the current context. The model isn't disobeying because it is malicious, it is responding to the strongest signals in what it sees. That is why defenders must control the context and constrain what the model is allowed to do with it. Tokens and attention come together inside the idea of a context window. The context window is the maximum amount of tokens the model can consider at once when generating outputs. If the conversation or document is longer than the context window, something has to give, and the model will not be able to directly attend to everything. Sometimes systems manage this by summarizing older content or selecting the most relevant parts, but that selection can introduce errors. The important part is that the model is not reading an infinite memory. It is working within a limited view. This limitation explains why models can contradict themselves across long conversations or forget constraints stated earlier. It also explains why repeating key constraints in a clear way can sometimes improve behavior, because you are placing the most important instructions inside the visible window. For security, context windows create risk because they define what the model can be influenced by in the moment and what it might ignore. An attacker can exploit context limitations by pushing harmful instructions into the visible region while pushing safety constraints out of it. Context windows also matter for data leakage risk, because what is in the context is what can potentially be echoed, transformed, or indirectly referenced in the output. If sensitive data is placed into the context, the model can incorporate it into the response, intentionally or accidentally. Even if the system is designed to avoid disclosing secrets, the safest posture is to limit what sensitive data enters the model's visible context in the first place. This is a core security principle. Reduce exposure by minimizing what is shared. The exam may describe a system that provides the model with internal documents, logs, or user data as context to answer questions. Your security instincts should immediately ask, who can trigger queries, what data is being injected into context, and how is access controlled. Context windows don't just set size limits. They define the surface area where confidential information can be handled. The more sensitive the context, the more careful the guardrails need to be. Now let's talk about limits beyond context size, because transformer-based systems have other constraints that matter for decision-making. One limit is that the model's output is generated step by step, token by token, based on patterns learned during training and influenced by the context. This means the model can drift mid-response, especially if the prompt is ambiguous or conflicting. It can also mean the model can produce content that sounds consistent but is built on an incorrect early assumption that compounds as it generates. In security scenarios, that can turn into confident-sounding misinformation or unsafe guidance, especially if the model is used to summarize incidents or recommend actions. Another limit is that the model does not have direct access to the outside world unless a surrounding system provides it, so it may fill gaps by guessing rather than admitting uncertainty. That guessing behavior is not a moral failing. It's a statistical tendency to produce plausible text. The defensive response is to design workflows that include verification and to avoid letting generated text become an unverified source of truth. Another practical limitation is that transformer models can be sensitive to prompt phrasing, ordering, and framing. Two prompts that are logically similar can produce different outputs because the token patterns and attention signals differ. This is why prompt templates and consistent instructions matter later in the course, and it's also why security controls have to anticipate variation. If a system relies on the model to follow a safety rule, but the rule is described differently each time, behavior can vary in ways that attackers can exploit. In exam terms, you might see a scenario where users can interact freely with a model and sometimes get restricted content through clever wording. A key insight is that the model's behavior is not a simple rule engine. It is a pattern-based generator influenced by the context. Therefore, safety has to be layered, not dependent on a single perfect phrase. You reduce risk with access control, filtering, monitoring, and design constraints, not with a magical sentence. It also helps to understand that attention is not a guarantee of privacy. People sometimes assume that if a model is focusing on relevant parts of the prompt, it will naturally ignore sensitive parts, but that is not how it works. If sensitive content is present, it can be relevant in unpredictable ways, and the model can incorporate it into outputs. This is especially important when systems include conversation history, user profiles, or retrieved documents. Even if the user does not ask for the sensitive data directly, it might influence the model's response. That influence can create subtle leakage, like revealing internal project names, customer details, or operational patterns that shouldn't be shared. In security thinking, leakage is not only about dumping secrets verbatim, it's also about revealing hints that help an attacker. Transformers are powerful precisely because they can connect dots, which means they can connect dots you didn't intend them to connect. Limiting context exposure and controlling retrieval are defensive moves that align directly with how transformers behave. From a defender's perspective, context windows and attention also shape how you monitor and test these systems. If a model behaves safely in short interactions but becomes inconsistent in long threads, that might be a context management issue rather than a core policy issue. If a model follows instructions until a user provides a long, complex prompt with embedded instructions, that might be an attention hijacking risk. If a model's responses change significantly when you reorder the same information, that might reveal sensitivity that needs to be handled by templates and guardrails. The exam may not ask you to run tests, but it will ask you to recognize which control is most appropriate given the failure mode. If the failure mode is about what the model sees and prioritizes, controls that manage context and instruction hierarchy are often central. If the failure mode is about output risk, controls that filter or constrain outputs become more relevant. Understanding transformers helps you choose answers that match the underlying mechanism. A common misconception is that context windows work like human memory, where the model remembers everything that happened earlier and can always refer back. In reality, the model's view is limited, and any sense of memory is often created by the surrounding system choosing what to include. Another misconception is that attention means the model is paying attention in a conscious way, like a person, when it is actually a mathematical mechanism for weighting influences. A third misconception is that if a model is trained on a lot of data, it will automatically be safe and accurate, when training scale can also amplify the ability to generate convincing but wrong statements. Clearing these misconceptions matters because exam questions often try to lure you into human-like assumptions about model behavior. The safe stance is to treat the model as a powerful pattern system operating within constraints, and to design and govern it accordingly. When you do that, you stop being surprised by behavior that feels weird but is actually predictable given the mechanics. To bring it all together, transformers are best understood as sequence processors that use attention to weigh relationships between tokens within a limited context window. Tokens are the internal units that define how text is represented. Attention is how influence is distributed across what the model can see, and context windows are the boundary of that visibility. The limits that matter for security flow naturally from those facts. Long interactions can push out important constraints. Untrusted content can hijack what the model prioritizes, and sensitive context can leak through outputs if it is exposed. You do not need to remember technical diagrams to use this understanding. You just need to apply it when a scenario describes a model being steered, forgetting rules, or revealing information. If you can explain in plain words why those behaviors happen, you are already ahead of many test takers. The exam is testing whether you can reason about risk in systems that look intelligent, and understanding transformers gives you the clarity to do that without guessing.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.